We'll wait for 2 more minutes and then I'll start. All right, so I'll share the screen for today's session. Before that, if you have anything to ask me or something, you can go ahead. I hope the screen is visible to you. So today, technically this is the week 12 session, but since I've also taken one additional session, so I've just for the count sake, I've written it as week 13. So today we'll be discussing the topics, like few topics from the week 12, and then after that, if time permits, if you have any queries or anything, you can just ask me. So once again, welcome to the problem solving session for the course Geographic Information Systems. The instructor for this course is Professor Reiki Saraf from IIT Roorkee, and I'm the teaching assistant Anshana from IIT Kanpur. So as I said, we'll be touching upon few topics from the week 12 lectures. With that, at least we can just we would have completed everything till now. So the first one is the applications of DEMS in viewshed and flood hazard mapping. Mm. So just a minute. Let me just connect my tablet. Okay, so first thing that we are going to discuss is the concept of viewshed. So what you have to understand is whenever we are talking about a terrain. So of course, now, by now you understand what a digital elevation model is, right? Because like that is what this course has predominantly focused on. So for any kind of uh, such analysis, where a terrain is involved, then what you have to understand is that from one single point, like you're standing in one single point, you cannot see every part of that terrain, right? Like for instance, if you're standing in a very flat region, like for example, you're in a football ground or something, that's a very flat region. There is no ups and downs, like undulations over the surface. In that case, you can see that area for a large area can be covered even if you stand in a single point, right? But what happens is our terrain is not so uniform in every place, right? So if you're standing in a single point, like a single point observation is not going to give you an idea of the entire terrain. Specifically, that's what I'm saying in case of an undulated terrain. Okay. So that is where you have to understand the concept of viewshed. It is basically the identification of areas of terrain that can be seen from a particular point on the surface. So first and foremost, you have to understand that like you're standing in a single point, you're not going to be able to see the entire terrain. Then what is the thing that you can do? Like you have to see if that what all regions of that terrain can be spotted from that point of like observation. Okay, so that needs to be delineated first, because any artificial thing, like see, we have natural things also, but any artificial thing or like any like man-made structures, like a tower or a building or anything. So for those when you're going to build that, this idea needs to be there. Like for example, this example was given by Dr. Saraf also. So it's basically like whenever you're booking a hotel, especially if it's a very expensive hotel near a sea or something like that, or in a mountain area. So people always like if they're ready to spend the money, they always prefer a room that or a hotel which has a good view, right? Like the region that it overlooks needs to be good. So for such thing also, this view shed analysis, that visibility analysis uh, is done so that like they can satisfy the customers and thereby increase their earnings. So that's the reason why anyone who is building such facilities like a hotel or some kind of watchtower in case of a forest area, so they would like to know like beforehand what would be the height of that building or a tower and how much area that is going to be visible if you build a tower or a building of that particular height. But the thing is, this needs to be done before it is built, right? Like you cannot just build one thing and then like realize that okay, this was not what it was supposed to be. So that is where this GIS comes handy, because here you can actually model it. You can model it before you build it, and then you can understand like okay, like if I do this, I can see this much. So such things can be done beforehand. Some sort of modeling can be done beforehand, and then only go ahead with the proper structure. So here in this image, you can see this is a digital elevation model input is there. So you can see this rugged terrain, and this triangle that you see here, this particular thing, that is the point of observation. That is what they have written here. That is where the observation tower is. So what this image is trying to tell you is that all these green points that you see around it, that those are the regions that are visible when when you observe that entire area from this watchtower or this observation tower. And all the red regions that you see, that is not in the view of that particular tower. So this was like determined based on this modeling rather than actually building that tower and seeing what all things you can see. So viewshed operation that uses the digital elevation model data, the DEMs. It can use the digital terrain model data or even the triangulated irregular network data, whatever it is. But it can, like, all these things are used in order to fulfill this requirement. So how are these view sheds calculated? They are basically like an observer point, like in the previous image you had seen. So we have a point of observation. So it uses the line of sight from observer point to the terrain surface to calculate the intervisibility matrix, like where all are the places that you can see. So that line of sight is determined. So the visible parts of terrains can be delineated, and the non-visible areas or the dead areas can also be delineated, like it was done in this previous image. So the red ones are the non-visible areas and the green ones are the visible areas. So what is the use of observation point and terrain offsets? Like for example, uh, like if there is a tower, then the height of the tower has to be added. Okay, because like it's not from the ground level, right? So it's at some height. So that height of the person or the observation tower also needs to be taken into account. Like such problems can be there. Like although we are modeling it, then such factors will also come into play. So this is the offset, like the intervisibility matrix. So here, this is the offset that we need to provide while we are doing the modeling. So here, if you provide the offset as 0, that means there is no because this human height is the one that is being considered. Okay. So when you say 0, then human height, the human height, just a minute. Okay. So yeah, what was I saying? Okay, we were discussing about offset, right? So when we say there is 0 offset, that means the human height or the height of the tower or whatever building is there, that is not added. Okay, here I'm just mentioning it as human height because here you have a person that is being represented here. When that is 0. But if the person is standing, then the offset of, like for example, if this is the case, then you have to add this offset also when you're uh, calculating the intervisibility matrix. So here basically you are seeing the visible areas, like this is the line of sight for this person. Okay, so this area, till this area it is visible for that person, so it's represented by the pink color without offset B, without this. Okay, they have delineated it with respect to this line of sight, but you can see the person cannot see this much area. Okay, so that comes under non-visible. Then again, it is visible because this is in the line of sight. Then again, it is not visible because of this depression. So like that, it's basically with offset P and without offset P. Like because if you consider this offset also, then whatever this side cannot observe, this side can. So that's why the visible region is more in the when the offset B is taken into account, and when the offset B is not taken into account, you have more non-visible areas. The only idea that you have to get from this is that we use the DEM, digital elevation model, in order to model the view shed. And what is the view shed? View shed is something which we use, like it is basically the areas that you can see in a terrain uh, from a point of observation, uh, and those visible areas and the non-visible areas are delineated. So here you can see this is a line of sight that you can see here. So if you can see that there are points in between that are not visible, because the green areas, they are the points that are visible, and the red areas will not be visible. If you can see here, okay, this is the line. Now if we change the offset, like we can change the offset, of course, like target offset, observer offset is there. So you can change the offset values uh, once changed, you can just reanalyze the entire thing. Then we can plot an XY profile, like or a profile all along that line, that will let you know in the line of sight, like which are the areas that are visible and which are not. So you can basically adjust this observer offset and target offset in order to reduce the non-visible areas that are present here. So if you change the offset from where you are looking, or the offset of the target, then most probably this red areas will decrease. Similarly, if you consider this, like here we were looking at a line of sight. Now here we are considering a circular area. Okay, this purple circle that you see here. This will become a typical view shed. Then like all these areas which are showing this light, this is like violet kind of color, uh, that would be visible, otherwise it's not. So this, wherever you see this light violet color, that is visible. Whatever you don't, or like which is not this color, they are not in the visible region. So now here, earlier you just had to give a observer offset and a target offset. But here you can see even the field of vision you can change. Like for instance, this is like 360-degree vision you have given. That maybe if you want to just have a 30-degree vision, you can adjust that. Even the like near distance part you can control, the far distance you can control. So according to your requirement, like how far do you want to see, or in at what angle or exposure you want to see, all those things can be adjusted in order to do this visibility analysis. This is a view shed around a single point. Earlier we had along a line. Here it is around a single point. Okay, that's why we have this circular region that is present over here. Now here, instead of a circular area, like we don't have, we have something like this. Okay, this is not a circular region. So the green areas, like this is the point of observation, and then you have these green areas with a particular offset. They would be visible. Otherwise, they will not. Okay, like according to that offset only, we can actually specify whether it is going to be visible or not. So all these details, like these visibility parameters that are mentioned here, they are very important. All these things, that offset, offset B, this radius, azimuth, all those things are very, very important in order to do the visibility analysis. It's always dependent on what you're looking for and in what way you're looking for. Like, is it from a point? Is it along a line? All those things. Here also it has been done, like instead of putting digital elevation model in the background, here we have the shaded relief model, which we had discussed earlier. And if you compare this, both of these, the digital elevation model looks a little better because it gives the feel of the terrain more. And this one, of course, it is showing such undulations, but this looks a little better, right? The one on the right. Uh, okay. So here we have an example. So here the view shed from, instead of just one observer, they have taken a view shed from 5 observers, symbolized with unique value, the number of observers that can see each cell. Okay. So the 5 observers are marked by a circle here. So this is one. Okay, 1 second. I'll just. Okay, this is one observer. This is two. This is three. This is four, and this is five. So you have 5 observers in total in this particular case, because till now we were just talking about a single point of observation, but even multiple observers are also possible. So if in this particular case, if you have 5 observers, these are the areas that would be visible, and the red areas are the ones that are not visible. That is why it's given low. In terms of visibility, when it is more red color, it is like 0, and when it is more towards the green, it is more visible. So here we are taking into consideration all the 5 observers. That's why the green area is slightly more, because like you are kind of getting the information from different locations. Even here you can see, right? It's classified in 2 classes, just visible and non-visible. Here we had a range. That's why here we have a variety of colors that you can see here. But here we just divided it into 2 classes. That's all. So there are different types of visibility analysis, like 2 types of visibility analysis that can be performed. Uh, the frequency, it determines which raster surface locations are visible to a set of observers, and the observers, it identifies which observers are visible from each raster surface location. So here the observer one, like if you take a look at here, we have the input surface raster and the observer features. So we have the observer one and the observer two. Okay. And their offsets with the visible area. So here we have the visible area, which is like represented in this green color. And areas which are visible to observer one, and areas which are visible to observer two, and also areas which is visible to both the observers. That is also represented in this image. So just the visible areas, if you are taking a look at that, this is what you get. Then if you specifically look for locations that are visible to just one and only by two or by both, that is also shown here. Then Sir had just slightly touched upon this digital elevation model based flood planning. Before that, okay, I just want to touch upon the uses of this visibility analysis. Like we know what visibility analysis is. So the uses of visibility analysis is that like there are several uses, few of which include the visual impact analysis, the landscape evolution, the siting of observation tower and cellular communication mast, like for the mobile tower, modeling coverage of cellular communications, military applications, like especially if you have visited these regions which are very close to the border or not, you see these watchtowers, right? So they're not just simply installed in that place. Basically, they're strategically installed based on such planning. So those things before they are kept there, such visibility analysis are already done in order to make sure that okay, like if you build such a structure over there, it's going to be worth it, and rather not just some random structure which is not going to be useful. So then that brings us to this portion, that is the digital elevation model based flood planning. So DEMS can also be employed in case of flood estimation. So of course there are like many other things which can be incorporated to have to get a very realistic picture or the real estimates of flooding or how much area is going to be flooded. So the geomorphological processes will also be required because these processes are active in floodplain areas related to terrain elevation. DEMS may provide a sound base for quantitative studies related with flood hazard. See, the thing is, if you are able to understand that terrain well, then you can actually understand how far, if, for instance, if a river floods, how far that water is going to go and how much it's going to go. Like such estimates can be done if you have an idea of how that terrain is, like how much undulated it is or how steep or gentle that terrain is. So, like DEMS will provide a sound base for quantitative study related with flood hazards. So, even if we have an urban area, we are getting a detailed digital elevation model for that area. We can predict a flooding scenario also. So, in such cases, historical elevation data are available. So, it's not just like an open area, like you can do this only in an open area, but you can even do this in a urban setting. The sedimentation and the erosion rates, they can be derived if we have the information about the terrain, uh, like old information as well as the information that you have as of now. Then we can understand how much of erosion, if it has increased or if it is stable or whatever it is. Such things can be determined. And like such things are possible now. That's the thing. Like it's not like you are estimating a lot. If you have certain information from the past and from today, we can more or less make a better or accurate uh, understanding of this area. So even if like you have like what do you say, a 20 years of time difference, you would know that along the river or flood prone area, like where that sedimentation is going to happen and where the erosion is going to happen. So accordingly, you can actually sort of uh, build this flood barriers and things like that, and thus preventing the impact of the flood event. And thereby they generate a flood hazard map. So if you have a map that is generated like this, so you can see the color gradation that they have given, like 6, 8, 10, and inundated areas. Inundated means where that water has come. So once you get an idea of how that flood is going to impact that region, so according to that, the rehabilitation, relocation, all those things can be done. So this is possible because we are using the digital elevation model and doing the flood planning uh, through GIS. So that's the benefit of having knowledge about geographic information system. Then another application of digital elevation model is in case of solar energy potential estimation. Just a minute. So this is basically to understand like how we can exploit these digital elevation models in order to estimate the solar energy, and even this has been done for wind energy also. Okay, so like using the DEM in order to understand how you can make use of the solar radiation that is coming onto the Earth's surface. So the incoming solar radiation that we get onto the Earth's surface, we call it as insolation. That of course we get it from the sun. Now, as it travels through the atmosphere, it will get modified. Like it's not like one single ray of light which is directly coming. That's not the case. It is further modified by the topography where it is going coming to and the surface features that are present there. It gets intercepted at the Earth's surface as direct, diffuse, and reflected components. So it's not like how you think, like you have the sun, and then sun's rays directly hitting on the surface. That is not how it is happening. Because we have an atmosphere, because we have a topographical difference, then, and we have other features present on the Earth's surface. This sun's radiation is going to come as one, as a direct radiation. It can come, then it can become a reflected radiation, like it hits a terrain, an undulated terrain, and then it reflects. Or it can be a diffuse radiation if you have the presence of clouds. Okay, so it's not like you just have a single ray of light that is coming. So if you have a clear sky, then the sun's radiation will directly reach the surface without any kind of disturbance or hindrance. But ideally, like that is a very ideal scenario. Generally, that's not the case. Like realistically, we do have the presence of clouds and everything. So this is more the picture that is shown here. That is a more realistic representation of how the solar radiation comes to the surface. And the reflected radiation that I said, that is more prominent in case of hilly regions. Okay. Then we have the surface features like vegetation, agricultural crops, or like some kind of soil conditions, like in the lithology. So all these things behave differently with the solar energy. So the solar radiation which is coming before it reaches the earth, it gets intercepted at various places, and therefore we have these direct, diffuse, and reflected radiation. So the direct radiation, it is intercepted unimpeded in a direct line from the sun. So there is nothing blocking it; it's just directly coming. The diffuse radiation is scattered by atmospheric constituents such as clouds and dust. So if you have the presence of clouds, if dust is present in the atmosphere, then the solar radiation is going to be diffused because of that. Then we have the reflected radiation that is reflected from the surface features, especially in the hilly areas. Okay, so reflected radiation that is more a constituent of the hilly regions. The sum of the direct, diffuse, and reflected radiation is called the total or the global solar radiation. So the total radiation is basically a sum of all these three. So it's basically, you can just imagine it like the sun's radiation, it comes and then it sort of splits. It's not necessary that it always splits like this. Like reflected radiation is more dominant in case of undulated areas. So if that is not present, then more or less you will be having only these two components. So generally, the direct radiation is the largest component of the total radiation, and diffuse radiation is the second largest component. Reflected radiation will be uh, contributing a little less when compared to the first. Just give me a minute. I think there is some problem with my screen sharing. I think it is fine now. And one more thing that you have to keep in mind is, like as I said, there are these three components of solar radiation, and the reflected radiation, because it's not so common. So generally in GIS, like the solar radiation tools, they do not include the reflected radiation in calculation of the total radiation. Like in certain cases, we might have to specify that, because that's not a very, what do you say, a very like important component that is contributing a lot to the solar radiation. That is the reason why we consider the total radiation, which I'm writing as TR, that is equal to sum of the direct radiation plus the diffuse radiation. So this you have to keep in mind, like although we have three components, but most of the time the total radiation is calculated based on the direct and the diffuse. Unless if a region terrain is largely influenced by the reflected radiation, we will not consider it. So the solar radiation calculation for point locations, or like for an entire geographic area, like if you want to do that in GIS, like Geographic Information System, then it involves these four steps that are listed out here. So first thing is the calculation of an upward looking hemispherical view shed based on topography. So upward looking is like basically it's sort of like facing the sky kind of thing. Okay, I have an image in the next slide that will give you an understanding what I'm trying to say. So first you need to have a hemispherical view shed based on topography, which is upward looking. Then you overlay this view shed on a direct sun map to estimate the direct radiation that is present. Then you overlay the view shed on a diffuse sky map to estimate the diffuse radiation. Then repeat this process for every location of interest to produce an insolation map. So it's a very like stepwise thing. First and foremost, you need to have the view shed. Okay. And how that, what is the specification of that view shed? Should be an upward looking hemispherical view shed, which is based on the topography. Once you have the view shed, you need to prepare a sun map, like handy, and then that sun map plus the view shed, like you overlay it. That is the first, like the second step. This is done in order to determine the direct radiation. Then what do you do? The next thing that you do is, again you overlay this view shed with the sky map. Sky map plus view shed. What will this give you? This will give you an idea regarding the diffuse radiation. Okay. So you got the direct radiation, you got a diffuse radiation. Now this particular thing needs to be done for every location of interest in that area in order to produce an insolation map for that entire region. So this is the fourth step that is done in case of solar radiation calculation for point locations or for an entire geographic area using GIS. This is what I meant by the upward facing viewshed, hemispherical viewshed. So since radiation can be greatly affected by topography as well as surface features, a key component of the calculation algorithm requires the generation of an upward looking hemispherical viewshed for every location in the digital elevation model. The hemispherical viewsheds are like upward looking photographs. Like if you take a camera and you click a picture like this, we call it as fish eye picture. So which view the entire sky from the ground up like the view in a planetarium. So here you can see, right? You can basically see the ground also. At the same time, you can see the sky also. So first we have the view shed. Then what did I say? Like in the next step, it involves that you get a sun map. Once you calculate the sun map, then you overlay the view shed with the sun map. So the direct solar radiation, which is originating from each sky direction, is calculated using a sun map in the same hemispherical projection as the view shed. So same projection we will use, and we will calculate the direct solar radiation that is coming from different sky direction. So effectively, what do you mean by a sun map? It is a raster representation that displays the sun track or apparent position of the sun as it varies through the hours of a day or through days of the year. Okay, it can be over hours when you consider a particular day, or if you consider a whole year, then it can be through the days of the year. So it's basically like you are standing on the ground. That's what they're trying to tell you. It's a hemispherical view shed, right? So you're on the ground and you're seeing the movement of the sun from one end to the other in that hemispherical pattern, how it moves across the sky over a particular period that you are designating. So this is a sun map. Basically, this is how a sun map will look like. So it is for 45-degree north latitude. Uh, and it is calculated from the winter solstice, which is December 21, to summer solstice, which is June 21. So it's like basically done for 6 months. Okay, so this is December and then June. Okay, so that much time period has been taken into account, and this is done for the 45-degree north latitude. So each sun sector, that is basically these colored boxes that you see here, they represent the sun's position using half-hour intervals through the day and monthly intervals through the year. So half hour is basically here you can see the time, right? So here it is written as 5. This is 6, 7, 8, 9. So that is coming basically after two such boxes. So it's basically one colored box is half-hour interval through the day and monthly intervals through the year. Here you can see. This is monthly interval. This is the time interval that you can see. It should be noted that the image is in the same hemispherical projection as the upward looking view shed. That is important because in previous classes also you might have seen in lectures that if whenever you want to overlay a map over another map, then it is very much necessary that the projection that both maps have should be same. Without that, you cannot do a proper overlay. So the same thing is done here. Like the image that you're creating here, that should have the same hemispherical projection as that of the upward looking view shed that you created in the first step. The position of the sun is represented as it moves across the sky during the time of day and time of year. That is why we have this time that is given here and the months that is given here. So this gives you the time of the day and this is the time of the year in terms of months. So from December we have till June. So this is how you generate a sun map in order to overlay with the view shed. Then we have the sky map. Why do we use the sky map? In order to calculate the diffuse radiation. Sun map was done to understand the direct solar radiation, and the sky map is taken into account in order to understand the diffuse radiation. So the diffuse radiation, it originates from all the sky directions as a result of scattering from the atmospheric components. Like you have the clouds, dust, all these things, all the particles present in the sky. So it's basically coming from all the sky direction. To calculate diffuse radiation for a particular location, a sky map is created to represent the hemispherical view of the entire sky, divided into a series of sky sectors defined by zenith and azimuth angles. So we have to first generate a series of sky sectors based on the zenith and azimuth angles. And each sector is assigned a unique identifier value along with these angles. So diffuse radiation is calculated for each sky sector based on the direction. So here you can see a sky map with sky sectors defined by 8 zenith divisions and 16 azimuth divisions. This is the zenith division, okay? 1, 2, 3, 4, 5, 6, 7, 8. And then if you count throughout the circle, you will see there are 16 azimuth divisions. Like for instance, here we have 1, 2, 3, 4, 5, 6, 7, 10, 12, 13, 14, 15, and 16. Okay, so we have 16 azimuth divisions and 8, that is 8 zenith divisions that are shown here. Each color represents a sky sector or portion of the sky from which diffuse radiation originates. So this sky map, not this, okay, this sky map plus the sun map plus the view shed together, when you put one on top of the other, you get an idea regarding the incoming solar radiation. Now, the application of this such solar radiation analysis, that includes like uh, like for example, if you have an area, uh, like you need to determine a site for a ski resort. Okay, skiing is basically where you have extensive snow layer present on the hill slope or something. So, if you want to build a ski resort, then you need to understand like how much of sun an area receives over a period of time, or in order to grow a specific kind of plant or a crop where a specific climate condition is needed. So for that purpose also you can make use of this solar radiation analysis that is done. Then, of course, predicting the behavior of forest fires and making decisions concerning the best firefighting methods. Because especially in extreme summer time, if the region gets really dry, the chances of forest fire is really, really high. So if you have an idea regarding the incoming solar radiation based on the solar radiation analysis, then some precautionary methods or can be taken. And even if in the event of a solar like a forest fire, further rescue and such steps can be uh, taken into account. Another example that sir mentioned was probably like, as I said, for particular crops, they sort of look into this, like in potential sites for vineyards, like for preparing the wine and stuff. So for that, this hillside, which hillside is needed. Such things can be chosen based on this information. Then, as I said, this digital elevation model that is also used for understanding the wind energy, like how effectively you can use the wind energy, just like how we are making use of the solar energy. This is especially like in hilly terrain. uh, this sort of plays an important role. In flat area, things can be different, but hilly areas, wind frequency, speed, all those things might be a little higher. So you can actually make use of that wind energy. Uh, Now I'll just share the slides that Sir had prepared for the remaining part, and then we'll discuss these problems. Just to have an idea regarding these errors in GIS and the key elements of map. Sir has also discussed the sources of digital elevation model, but that is like he has given a lot of information in that. So if you're interested, you can go through that part. But I thought this would be a little more worth discussing. So first and foremost, these are some of the things we've already discussed, but it's better that you go through it again. So errors in GIS, like of course we are generating maps and everything. That is the output that we get, right? Once you do the analysis and things. So even then, those can be prone to errors also. It's not that it is completely error free. So in order to understand the errors in GIS, you need to have an understanding regarding precision and accuracy. So precision is a statement of the smallest unit of measurement to which data can be recorded. How precise, like how much, closer or the smallest unit of a particular data can be measured is what you call it as precision. And accuracy, it is a statistical concept which states the likelihood or probability that a particular set of measurements are within the certain range of true value. Like you have a true value, and if you have other measurements which are very close to the true value, we say that those measurements are accurate. Okay. Instead, this is where I think Sir has given that diagram. I had shown that example also with the bullseye, right? Like you have, okay, so if you remember, I had drawn that image like this for you to remember this concept. So you can have, let's say, precision, then you can have accuracy. Okay. So here, this is something which will be useful for you to remember. That's why I'm just drawing it again, because this has been mentioned quite a few times throughout these lectures. So it's better that you keep it in mind. So if you have, let's say, something like this, like a dartboard or something. So you have something like this, and the measurement points are scattered, or like this. Okay, this means, and let's say this is like the origin. So when you read a graph, what does this mean? This means that this is having low precision, and it is also having low accuracy because that is close to zero, right? Now, if I have something like this, okay, now I have several points which are, okay, just a minute. Okay, very closely packed like this. We say, okay, my axis has changed. Sorry. Uh, or else I'll just erase this and draw a comment. Uh, if I have something like this, okay, so this means this has high accuracy, but the precision is low. Okay, low precision. Then we can have another one, which is again high accuracy, and at the same time it has high precision. Okay, because it is closer to this end. So which means all the points will be somewhere very close to the bullseye. So this is high accuracy and high precision. Then we have something over here which has high precision but low accuracy. So here high precision but low accuracy. So here what happens is you have a set of measurements which are very close to each other, which means the measurements are precise, but they are not close to the true value. So they are not accurate. That's the idea that is being conveyed here. So how far away from the mark you are is described by accuracy, and how well you measure is described by the precision. Okay, the same image is here. So if you are precise, that doesn't necessarily mean you are accurate. However, if you are consistently accurate, that means you are also precise. So just because you have a set of values which are very close to each other, uh, which tells you that you have a high precision, that doesn't mean that those values are true. But if you have consistently accurate measurements, then they can be precise also. This is another way that they have represented what I drew there. So it's accurate and precise because everything is in the bullseye. Not accurate, but it is precise because these values are close to each other, but it is not close to the true value. And then it is neither accurate nor precise because all the values are scattered. Maps and other data used in GIS are obtained by measurements, and therefore inevitably they contain errors no matter how small. Because see, in GIS we are using a lot of data, right? And these data you're getting it from different sources. Now it's not possible that all these data that you get is error free. Like there can be some sort of error that is present. Even like when I said like um, when we make use of some image or something, or like some satellite image, something like that, the position of the satellite, the time when it was taken, such things can induce some sort of error in that image. So it's not always in your hand to get very error-free image. Only thing that you can do is manage those errors. So GIS users, as GIS users, we need to understand inherent and operational errors and how they will propagate. That is also needed. Like if that error is just staying there, then that is fine. But throughout the process of this modeling, if it is going to continue, like you have to have an understanding about that also. So that is not something which has been entirely understood even now, because of course it's a very, very developing field. So as you understand it more, as you use it more, only then such errors can be understood better. It's not possible to remove the errors all the time, but we can manage it and keep it at the minimum. So what are the sources of error? Like we said, errors are there. So where do these errors come from in case of geographic information systems? So the source of errors include the geometric and positional errors, like the position, if that calculation was mistaken or something like that. Classification errors in the remote sensing data, the field data sampling or the ground control points. Like when you're choosing the ground control points, if some error has happened, of course, it's going to affect the georeferencing, right? So it's kind of like continuing. So that kind of thing. Then that is like source. In case of source, what all errors can come. Then when you input the data, what all errors can come, like digitizing errors can happen. Okay, when you're digitizing some data. So the person who is doing it can make some mistakes. The precision with which you're doing it could bring in some error. How you are entering the attribute data, that is also an error possible. Then errors due to wrong band identification of the remote sensing data. So such things like this is how you have errors from the source data and you have errors from the input data. Then it comes to data storage. So if limited precision is there, uh, like the problem with data storage is that due to limited precision with which coordinates and other numerical data are stored, because like as I said, like in the previous sessions, like if you convert from one format to another format, visibly it will not have much problem. It will be more or less what you had before. But when you get into the details, only then will you understand that there might be certain cells or grids which are not accounted for. So such things, like, and why do we do that? In order to manage the storage, right? So that therefore there can be errors in the data storage. Then in data analysis and manipulation, error propagation can happen when you do the map overlay. Then incorrect use of logic or equation or interpolation errors can also be there. Then errors in data output and application. Cartographic error due to the limitations of output devices and the incorrect or inappropriate application of GIS products. So basically from this, what you have to understand is that there are multiple sources of errors, possibilities of errors, which you have to manage and bring it to the minimum, because it's so huge that it may not be possible to make it completely zero as of now, but at least you can bring it down to the minimum. What all good maps should have. So essentially the output that you get from any kind of analysis is a map, right, in the GIS. So irrespective of the style or the content of the map, there are certain things that every map should have. Okay, that's what is known as the golden rules of cartography. So the first and foremost thing is the title. Like it should give you information about what that map is telling you about. And that title should be always represented in a very large font, easily identifiable, and descriptive text should also be there, telling you which location that is and also what is the purpose of that map. Then we should have a scale indicator. Why do we need a scale indicator? Because, for example, you have this India map. Okay. So when you just give a map without any scale, it's not possible for us to understand how far, like if you're just looking at, let's say, some sort of a seismic zonation map, which is telling you about the areas that can, different seismic zones, uh, earthquake affecting areas and all. So if you don't understand, if you don't give a scale for that map, a scale is something which you always see at the bottom of a map. Okay. So if you don't have a scale, we will not understand how far or how much of an area that zone is covering. Without that, basically no information is there. So a scale is very, very important in case of a any map. Okay. Then orientation, of course, like where the north direction is, that needs to be shown. Then it can be like there are numerous styles in which you can show it. Basically, you just have to show where the north is. Then, of course, a border needs to be there where the map area stop, like where that complete thing stops. The distance between that map and the border should be the same on all sides. It should be balanced. Now the benefit is that earlier this was done very manually, but now because we have GIS like softwares like QGIS, ArcGIS, you just have an option where you can give the border just like that. Okay. And then of course we need a legend which defines the symbols or colors. It include shades of gray and patterns used on the map. Maps do not need legends if the symbology is so common or as simple as to be easily understood. Then, of course, if you have, um, you know, taken this map from somewhere else, then that credits needs to be given, like source, the name, date, all those things. Locator map is basically, for example, if I am taking a region, a district area or something from the India map. So just by giving that district area, it may not be understandable by everybody. So in the inset, we will give a India map also. So that that is the complete picture, and then from that you are selecting an area, that kind of thing. Then of course it should have a effective graphical design. This brings us to the limitations of GIS. Uh, like we have talked about a lot of benefits that we get out of geographic information system, but at the same time we need to also understand that there are certain limitations associated with the geographic information systems. So it is expensive. Sometimes paper atlases or maps are cheaper and easy to handle because, as I said, we have few free GIS softwares like the QGIS, but ArcGIS, which has a lot of options, it's like it requires a license, it needs to be purchased, so it's not very accessible to everybody. So, in comparison to that, if you have a paper atlas or some map, uh, that is more cheaper. So it's expensive. Then it requires too much data and that too in digital format. Data requirement is really high. It's computer intensive and therefore it might require a lot of storage. That's why like all the time we emphasize that unless and until it is very much required for you, uh, don't use very, very high resolution data just for the sake of it. Only use it when you actually require it. Otherwise, if you can make do with a medium resolution image or information data, that is fine. That is the only thing that you have to use. GIS spatial databases are software dependent and hence their exports and imports are very limited. The databases that are available, it is very much dependent on the software. So how you export it or import it will be dependent on the software that you are using. Then of course this copyright distribution that everything, it's in such ways there are certain limitations for the geographic information system. And then of course the output that you get, most of the time you require a computer to see it and understand it. And if error has propagated throughout the analysis, then that is going to give you very erroneous, like difficult to understand kind of results. So these are some of the GIS rules, like there is no particular scale for the digital data that you are using. And as I said, like when you in LULC or in any other thing, when you classify, we make use of colors, right? But the colors also do not have any meaning in GIS. What really matters is the code value of the object or the feature. Like you can use any color, but then you have to specify like what kind of object is it, what kind of feature is it, what are you trying to uh, interpret out of that. Error propagates in GIS. So error should be checked at every stage of processing. This has been emphasized from the beginning. Like there are multiple steps that you're doing, right? Starting from obtaining the data, then cleaning the data, combining the data. So at every single step, it is better. Like in order to avoid this error propagation, it is always better that at every stage of the processing, you are keeping a check on the error, so that at least even if the error propagates, it's not so high that you get such very random results, which is not useful. Rather, it will be cut down to the minimum. And zero, the number zero, it is a value in GIS and it does not mean no data. So no data is like you cannot represent it by zero. Straight line should not be digitized. Only coordinates of two endpoints are digitized and connected. Never digitize a line, polyline, or polygon twice. And do not completely depend on export and import tools available in GIS softwares. These may change the coordinates of your data set. Like these are some of the rules that you have to keep in mind whenever you are uh, using the GIS software. This is just a random information that has been given here. Like if the term geographic information system is still valid, kind of that you can just go through. I guess now we can actually discuss the problems that I have, because we don't have much time also. So you can just give me the answers in the chat box. I will just show the questions. Like you have already done these questions, but I thought it would be better if we just revise them. The shape of a cell of a digital elevation model can only be which of the following? Rectangular, circular, square, triangle. You can just put the answer in the chat. Okay. So the answer is square. The overall shape of a digital elevation model can only be which of the following? Yes, the answer is rectangular and square. So here, the difference between these two questions that you have to understand is The first question, they are telling you the shape of a cell. What does that mean? Like in a digital elevation model, let's say this is every time I've mentioned it, but I'm just saying it again for keep like, sake of understanding. So basically, you have a grid like this. Okay. So what effectively they are asking is what is the shape of a cell? Shape of a cell is this. Okay, a single cell. So that is square. But the overall shape of a DEM, it can be either a square like this, or it can even be a rectangle. Okay, so that you have to keep in mind is that the cell will always be a square, but the overall shape can be either a square or a rectangle. An 8 bits DEM can have dash total number of positive integer values. No, the answer is 256. See, when you say this 8 bit, like if I remember correctly, the formula is like this 2 to the power n. Okay, so this n is basically the bits that are given. So 2 to the power 8 bits. So 2 to the power 8 is basically what? You can calculate it and see. So that will be 256. Okay. So for example, if it was uh, let's say 2 to the like if it is a 6-bit DEM, okay, it's a 6-bit DEM, then we will give it as 2 to the power 6, which is basically 64. Or let's say if it is a 7-bit, like basically 64 is 2 to the power 6, okay, and 128 is 2 to the power 7. And what is this n that is given here? That is the number of bits the DEM has, and this is 2 to the power 8. And I don't I'll have to calculate it how much this will be, but yeah, it is always in terms of 2 to the power the number of bits. Okay. I hope that is clear to you. So you can make use of this formula if such question comes. A DEM that shows finer details is said to be of what kind of resolution? Yeah. So finer details means as clear as possible, and that is basically high resolution. So a DEM that shows finer details is we call it as high resolution, and the one which is like very on the surface and doesn't give that much details, we call it as poor resolution. Which of the following is not a raster data structure? Yeah, the answer is spaghetti. Okay, that is not a raster data structure. Like this is from one of the previous lectures where we had extensively discussed about the run length encoding, quadtree, block encoding, and all those things. So that was basically regarding the data raster data structure, right? So spaghetti is not a raster data structure. Which of the following is advantage of the DEMS over the TILs, like the triangulated irregular networks and the digital elevation model? So what is the advantage of the digital elevation model? It's basically this DEMS, they use a simple data model. That is it. Like it's more less sort of complicated when compared to the triangulated irregular networks. The accuracy of a digital elevation model created from DGNSS data will be low. Is this true or false? This is false because basically this DGNSS, that is like GNSS, right? So DGNSS is basically differential global navigation satellite system. Okay, so this is basically an enhancement to the standard global navigation system, basically, which is the GPS that we use. So it's an improvement to that GPS, which actually improves the location accuracy by using reference stations at known locations. So it is actually an enhancement of the GPS. So the statement that accuracy of them created from DGNSS will be low is wrong. It is false. A surface significant point in a tin model is one which can be closely interpolated from its neighbors. No, that is not the case. The surface significant point in a tin model, uh, it's not like basically the statement is false because in a triangulated irregular network, this surface significant point, or we call it as SSP, okay, that it refers to a key point on the surface that captures essential geometric or topographic features. So it's not interpolated from its neighbors. It's a like a very specific key point that is used in case of triangulated irregular network. These are very crucial in defining the shape and structure of the terrain in the triangulated irregular network. So the statement that it is interpolated is wrong. Spatial resolution of a digital elevation model is it is fixed once the DEM is created. Like once the DEM is generated means you have already fixed the data resolution and everything that you had used, right? So it's not possible to make further alterations in the resolution of the digital elevation model. Just give me a minute. My pen is not working. Okay. So the reason why we say that it is fixed is because when you generate the DEM, okay, when you create the digital elevation model, like from any kind of satellite image or anything, at that time, the Earth surface is sampled at specific intervals, right? Like sampling has already been done at a particular interval. So that interval will determine the spacing between the elevation points and everything that comes later on. Cell size that represents the area. So everything is already like from that beginning itself, it is already fixed. So then if you try to alter the resolution, you're basically stretching the data. So it's not going to give you any improved results. You can do some resampling or something like that, but then it is not going to increase the detail that is already given in that digital elevation model. It just interpolates from the existing data. So it's always dependent on the original data that has been collected and used for creating that digital elevation model. DSM is a surface which can be used to represent which of the following. Yes, the answer is D, which is all of the above. So you can digital surface model, so you can use it to represent the groundwater levels, the quality of chemical quality of soil, and the chemical quality of water. So all this is possible using the DSM. Okay, so those are the questions that I have with me right now. So that is all. So if you have anything to ask me or anything, you can ask. Otherwise, this is all that I have.
Ma'am, I had an just an query like what type of questions would be asked from us like in the final exam, like the same as we had attempted in our assignments, like pattern would be the same.
As far as I know, I think it would be largely MCQ type only because I don't think you are having online exam, right?
Yeah, I guess it's computer based.
Okay, it's computer based, so I don't think you will have to expect very, very large problem kind of thing. But the thing is, like for example, in this raster case and all, we had discussed about the run length coding like that things, right? So
Yes,
when you
ma'am.
study, I don't think you have to like just focus on the straight answer kind of thing like MCQ type. You should also learn to solve certain things like that also. Like I would
Sure, ma'am.
suggest that because I'm not sure. Of course, I have not seen the problems for the previous exams, but that is something I expect. It's possible. So
What
don't
if
just.
we
Mm,
what if we want to refer like PYQs from where we can, or it would be like enough like we had done as assignments and the questions you had taught us, that would be enough like to refer type of the way we can go for our
exam.
examination pattern.
Okay, so what I would suggest for your preparation is like you have all this 12-week assignments, right? So go through all the assignments and from basically the idea is that once you start doing the repeating the assignments, you will get an idea as to how the questions were framed. Because when I went through each of the problems, what I understood is it has been taken from some portion from that lecture. So you will get an idea like how it has been they have prepared it. So basically when you go through the skim through the lectures, you will understand which topics you can avoid and which you can take. So I would suggest that go through all the week assignments once again. And of course I have also given few extra questions in the assignments that I have also discussed.
Yes, ma'am.
Those extra questions also you can have a look at it because those have been used in the past sessions like past year. So if they are not discussed now, then probably you can expect that in the exam also, right?
Okay, ma'am. Thank you so much, ma'am.
Sometimes it might be repeating also, but I've not seen the exam questions per se. That's the reason I cannot say for sure, but I think this is how it is going to be.
Okay, ma'am. Thank you, ma'am.
Okay, thank you. Okay, so that is all that I have for today, and I'm really, really thankful to all of you, like for attending the sessions and uh, contributing to the sessions. So thank you so much, and hope you have a really good exam, like you're able to do it well. So thank you so much.
Thank you, ma'am.
Okay.